Okay, so we are back, and a little bit late for those of you who are following us on streaming. I was making a joke now with Christian about some people in Riga now telling me, sending me WhatsApp, it's 3:20 whatever, and there's nobody there on the streaming. What's happening there? Of course, these persons are German, you know, so they are used to follow a strict schedule. So it is my pleasure to introduce Christian Blum. He's also German, although now he's half Spaniard. So Christian is, I think, we can say, is probably one of the top researchers in Metaheuristics that we have now in Barcelona and probably in Europe. So he has an outstanding CV. He's now working in the CSIC, which is the Spanish Center for Research, and yeah, I think his research is parallel in terms of what I know, because, you know, so I know a lot of people, but I think I know just a few people like with his CV. So it is my pleasure to introduce him. He's going to talk about colony optimization and hybridization of Metaheuristics. So Christian, thank you for being here.
Introduction. Well, maybe you're surprised to see the keyword and colony optimization there, because this was not announced. So it was announced that I would talk about hybrids only, but yesterday Joan was one of them who suggested that someone talks also about other metaheuristics other than ILS and VNS, because Celso Ribeiro, as we know, he cannot be here, and so we have a lack of introductions, let's say, into the basic metaheuristics. And I hope with the organization that's okay that I take 45 minutes for talking about ACO. If it would be not okay, this is the only set of slides I have. So. Okay, so I will take 45 minutes, 1 hour for that, and then talk about hybrids in a reduced way. Okay? Okay, so let's just have a look at the outline. So I will start with swarm intelligence, actually, before I go to colony optimization, which will be a basic introduction. Okay, so for the ones who know already how it works, probably in this part, you will not learn anything new. Okay, but then we go to the first hybrid. So this is the bridging subject, if you want, to the hybrids, because this hybrid is a hybrid with colony optimization. Okay, colony optimization and beam search, which was mentioned this morning by someone. And then I'm going to talk about two hybrid algorithms. The first one is a very standard algorithm, large neighborhood search. You have heard this keyword LNS, or large neighborhood search, also in some of the talks already, but I'm not sure if everyone knows what that is. So there, in this part, I will give you an example of what that is. Okay? And the last part is, for me, the most interesting part, because it deals with one of our latest research subjects. Okay, so this is a hybrid algorithm also, which uses an exact technique within a metaheuristic, if you want. And it is an algorithm which is a general algorithm for optimization, and which is, in a sense, complementary to large neighborhood search. Okay? Okay, but let's start with swarm intelligence. So what is swarm intelligence? We could say, in a nutshell, that it's an AI discipline, artificial intelligence discipline, whose goal is designing intelligent multi-agent systems by taking inspiration from collective behaviors. Okay? Collective behaviors of social insects, for example, like ants, of flocks of birds, or fish schools. Okay? So these are just some examples. Here we have 3 images. So on the left-hand side, we have a termite nest. You see that this nest is quite large. So you see that person standing there. So this nest has a height of around 5 meters, I would say. It has an incredibly complex internal structure. Okay, so there are some rooms or chambers, or how you want to call that, in there that have over the whole year the same temperature, for example. So it's a very complicated thing. And this is built by insects who don't know actually how to do that. Okay, they don't have the brain power in order to know what they are actually doing. So they are doing that with a swarm intelligent mechanism, following simple rules, local rules, okay? So reacting to their local environment. The same is the case for migrating birds. So in the middle here we have, I think these are geese probably. When they migrate, ducks also or seagulls fly in this way, they are building this V shape, okay? And this has evolved over time, this behavior, for some reason. And the reason in this case is energy saving, okay? So as a flock, they save energy. They don't always stay in the same position, so the first one will not always fly in this first position, because otherwise this one would lose all its energy, okay? So they change positions, but they're staying in this V shape, and as a flock they can save energy in this way, okay? Also, this is a result of following local rules, okay? Looking what your neighbor is doing and reacting in certain ways. The third example I've put here is the one of fish schools. So for sure you have seen that either live or in the water or on TV, that these fish schools, they are moving seemingly all at the same time in the same direction, okay? So it's really nice to see. This is also swarm intelligent behavior, because they are looking what their neighbors are doing and doing exactly the same. This behavior has evolved as a protection against predators, because when a predator sees such a fish school of hundreds or thousands of fish which move in this way, they cannot decide which one to pick. Okay, so it's very difficult to decide for them which one to take. Okay, at the end, often they cannot catch anyone because of this reason. But these are examples. Okay, so in general, these swarm intelligent systems, they consist of a set of simple entities, okay, like termites, ants, bees, and so on. These systems, they work in a distributed way, so there's no global control. Actually, until the 50s, the biologists thought that there is a global control. For example, in beehives, that the queen would actually know everything, would know how to do everything, and would give orders when to do certain things. But this turned out to be completely wrong. Okay, so the queen in a beehive doesn't know anything more than a worker, has just a different function. And the self-organization, so this distribute, they work in a self-organized way. Okay, and this self-organization results from different ways of communication between the entities. Okay, so we might have the direct communication. So ants, for example, when an ant finds a large object and cannot carry it to its home, okay, let's call it like this, then it recruits other ants for carrying. Okay, so these other ants will help then carry this object, or they will cut it into parts, and then everyone carries one piece. Okay. On the other side, and this is the important way of communication for self-organization, is the indirect communication. Okay, so this was labeled by a French biologist in '59. This was labeled stigmergy. Okay, and this graphic here shows you basically how that works. So these E's here, they mean environment, and the index is at a different time step. So this is, let's say, the environment at some initial time step for that behavior. Okay. Then this, the environment being in this state triggers a response of the colony, okay? This changes the environment. This changed environment will again trigger a different response, okay? And so on, until the environment at the end is in a state where the problem is solved, okay? Nest is built, for example, okay? So in this way, these societies of simple entities, they can solve complex tasks, but they do it in cooperation. They do it in a very different way than we do that, okay? At least, well, we have somehow both ways of solving these type of problems, but we would solve these problems in a different way, okay? Simply because we have a completely different brain power. Okay, so many swarm intelligent behaviors, they are based on social insects, okay? And social insects are basically ants, termites, and some of the wasps and bees. Now I want to go into some of these examples at least, okay? Now that we have less time, I have to cut even more. But But let's have at least a look at some of these examples and see how they are used, okay, in technical applications. So first one is cemetery formation. So ants, what they do is when they find the corpses of dead ants, they pile them together, okay? So they are tidying up, basically. They're piling them in so-called cemeteries. And this is a graphic which shows an experiment where the ants come out of this hole in the middle here. They cannot leave this circle. And the black thing you see there, these are corpses of dead ants, okay? So they're coming out, they're walking around, and then they have basically two behaviors. When they find the corpse of a dead ant in an area where the density of corpses of dead ants is quite low, so there are not many other corpses around, then the probability to pick this corpse up and carry it to some other place is high, okay? The other thing is when they are carrying a dead ant and they are reaching a place where the density of the corpses of dead ants is rather high, then the probability of dropping it there grows, okay, in function of the density. So this over time, you see that these are time steps here, A, B, C, D. You see that over time you have small piles here building up, and at the end, if you would leave that run to the end, you would have one big pile somewhere, okay? And this behavior, well, this has been, you can imagine for what that has been used, especially for clustering, okay? So this has been used in clustering applications, and here these are two examples, okay? You don't have to write that down. I will provide the slides at the end, so you don't have to copy anything quickly now. Okay. Another behavior which is often used is the way they divide labor, okay, or also called task allocation, and you find that in ants and some of the bees. So the problem is that, for example, in ant colonies, and in any colony of these, there are a number of tasks to fulfill, okay, at any moment of time. Examples are brood tending, foraging for food, maintaining the nest, tidying up, okay? But of course, it depends on the current state, okay, of what is more necessary. At some moments in time, brood tending might be more necessary than foraging, okay? If they have the storage spaces full of food, then maybe it's not necessary to do more foraging, okay? So this requires a dynamic allocation of the individuals, of the ants, to tasks. In principle, if we would imagine how to solve that, we would say we need a global assessment of the current state of the colony in order to do that, okay? They do that in a different way, okay? And this way has been modeled by means of response threshold models. Okay? And these models, basically, they work as follows. So let's say we have m tasks which have to be fulfilled, okay? And we have n individuals in the colony. So each individual I has a threshold delta ij for each task j. Okay? This is the threshold which has to be, which says basically how probable it is that this individual will engage in task j. Okay? There's also a stimulus for each of the tasks, and this is the probability that an individual I will engage in task j, which depends on the stimulus of the task and the threshold of this individual for engaging into task j. Okay? So this means if the stimulus is small and this is high, then the probability is very low to engage into this task. The other way around, if the stimulus is very high and this is low, then the probability is high. Okay? But these response thresholds, they're also dynamic. Okay? So for each of the time steps delta t, okay, we can measure the fraction of time that an individual I has spent on task j. Okay? And depending on this fraction, the response thresholds are changed. Okay? So this is a dynamic system, and in this way, the colony, let's say, adapts to the current needs of the of the colony. Okay, so the individuals adapt to the current needs of the colony. So these models, they have been used, for example, in self-organized task allocation. Okay, dynamic scheduling. This is the same, self-organized task allocation in a different application context. Okay. Okay. Next example is on fireflies. Okay. Maybe you have heard about Firefly algorithms and these kind of things, but for sure you know what fireflies are. These are small insects that emit a light pulse periodically. Okay. And in summer nights, I don't know here actually, I don't think we have fireflies here, no? But in Brazil, for example, I know that they have a lot of fireflies. So what they do is they synchronize, okay? They synchronize their light pulses. So at some moment, when there are many fireflies together, they will all emit their light pulse at the same time, okay? And this has been modeled by means of pulse-coupled oscillators, okay? And so this is the period, T is the period which every firefly has to emit its light pulse, okay? So when it emits here, then it waits T time and emits its next light pulse, okay? But if it perceives in its local area another light pulse here, let's say, then it doesn't wait the whole period T, it moves its own light pulse closer to the one it has perceived, okay? And with this simple mechanism, they are synchronizing. Okay? So you can imagine how this has been used. This has been used in distributed systems, basically like sensor networks, okay? Where they need, for example, time synchronization. Okay? Another example is nest construction. You have seen already the termite nest at the beginning. So here we have a termite nest, here we have an anthill, and these local rules the insects follow in order to construct, they are being used recently for automated construction, for example. I know that NASA, I don't know ESA, but NASA, for example, is working on things like how do we colonize Mars. Okay, and for doing that, they envisage that you send there a whole colony of small robots, and these robots, they would build actually the environment that humans would need when we are able to send them there. Okay, and so you need small robots, colonies of small robots that use self-organization in order to construct, for example, the buildings that people will need there. Okay. And of course, all these kind of research is in its very early stages, okay? So they are nowhere near in order to build buildings, okay? So, but they are doing, well, this is basic research, okay? And who knows what's coming out of that in 10 or 20 years? You don't know, okay? Also automated shape formation, this is something which goes into the same direction. There are also people in swarm intelligence working in animal-robot interaction, okay? So this is a research area which is very much related to biology, okay? So there are biologists, computer scientists, artificial intelligence people working in this area. They study the behavior of the animals, they try to model this behavior, and one of the applications they are already into, okay, apart from the next slide, if it works. This is about fish, okay? This is, in this example, this is an artificial fish here, okay? And they try to control basically a fish swarm with this artificial fish, okay? I'm not sure if there's already some reason behind that or some idea, but they study how to do that, okay? And for that, of course, you have to know exactly how these animals behave, what reactions they have, and so on, okay? But one really important application is that, so I don't know if you remember, a few years ago, there was this case in New York where an airplane took off and a bird was impacting into the turbine, and the pilot had to land, okay? Could not reach an airport and had to land in the river. And in this case, no one was hurt, but in our case, this might be fatal, okay? So it's really important that you don't have birds flying around when an airplane starts, okay? And they try to have artificial falcons that chase away the birds, okay? So this is also going into this direction of knowing how these birds which are there, how they behave, and how they can be, well, how they can be chased away or guided away, okay? You can, instead of a falcon, you can also imagine one of their kind which takes the lead and guides them away, okay? Okay, flocking is another application. So actually, this is one of the oldest studied swarm intelligent behaviors, okay? The definition is it's a collective motion of a large number of self-propelled entities, okay? And the oldest model, as far as I know, is this one of Greg Reynolds, the Boyd's model from '86, which works basically on, with 3 rules. So the first one is separation. So when the birds, for example, when they come too close to each other, they are repelled, okay? Alignment, so steering towards the heading of your neighbors, such that everyone flies into the same direction, basically, at the end. And cohesion, so steer towards the average position of your neighbors. So when they are flying to different directions at the beginning, and there are nice models for that, but you see that at the end, they will come together and fly into the same direction, okay? Okay, so these kind of things, they have been also used for clustering. But also there's one of the metaheuristics, actually, which is called particle swarm optimization, which is one of the newer metaheuristics. It was introduced for continuous optimization, but nowadays you have also versions for discrete optimization. It's debatable if these are really necessary or useful, but you have them, okay? So this is one of the metaheuristics, actually, which takes its inspiration from the flocking behavior. Okay, and the last thing leads us to ant colony optimization, the last example. Okay, this is the foraging behavior of ants. So I was talking about direct communication already. So when the ants find a large prey, they help each other in carrying this away. Okay, this is actually chorizo. Okay, we were in Aragon making some holidays, and one of the piece of chorizo was falling out of my sandwich. And these really large ants, so they measure more than 1 centimeter, I would say. They were incredibly quick in finding that, recruiting others, and then carrying this away. Okay, so this is you don't see that because of the photo, of course, but this is already in movement. Okay, when they were carrying that away. But the inspiring behavior of ant colonies is based on indirect communication. Okay, via chemical pheromone trails. So when ants walk, they leave a chemical which is called a pheromone on the ground. Okay, droplets of this pheromone. And when they have to decide for a direction, in probability they take the direction with a higher pheromone concentration. Okay, this pheromone also evaporates over time. Okay, this is another aspect that we have to know. And this leads to the fact that these ant colonies find not necessarily the shortest paths, but short paths between food sources and the anthill. Okay? So there were biologists, they have done experiments of that kind. This is called the double bridge experiment, actually. This was done in reality by biologists. So they have this anthill here, the nest. They have one food source, and then there are 2 paths, okay, for reaching this food source. One is shorter, and the other one is longer. At the beginning, of course, there's no pheromone in the environment, okay? So when they leave the nest, in probability, 50% will take the short path and 50% will take the long path. In reality, they are not goal-directed, of course. They will turn around, and there are videos about this, okay? But at the end, it will work. In a symbolized way, I show it always like that. So they walk then straight to the food source, and of course, these three here arrive first, okay? So while the other ones are still on the way, these ones take some food and already decide for a path to go back. And then there's already some pheromone on the short path. So in probability, more will take the short path than the long path, okay? As this pheromone, which they lay on the ground, also evaporates, at the end, this system will converge with a high probability to the short path, okay? Now, based on this behavior, there's the Colony optimization meta-heuristic, which I'm going to explain now in a simple version, okay? So which explains the basic idea. But first of all, we want to simulate this double bridge experiment, okay? Let's see how we can simulate that technically with a graph, okay? So we have a graph with two nodes. One is the nest, one is the food source. We have two links, E1 and E2, and this is the length. So one has a length of 1, the other one has a length of 2. We have a short and a long link or edge. And then we introduce a pheromone parameter for each one of these edges, okay, with their values. These are the values of these parameters. And they are initialized to some small constant c. This is the first difference to the real world, where we don't have any pheromone in the environment at the beginning. Okay? Here we initialize them, all the values to the same constant. Then we iterate this simple algorithm. Okay? So we place a number of NA uns in node A, in the nest. And in each iteration, these NA uns, they have to traverse from A to B. Now they can do that traversing link E1, which is the short one, or link E2. Okay? And now, using these pheromone values, we create probabilities, okay, for taking these links. So the probability is for the link E1 is the pheromone value on this link divided by the sorry, I don't know if it's the pizza or divided by the sum of all the pheromone values of all the possibilities. Okay. So with these probabilities, each one of these artificial uns takes one of the two links, okay? And then what we first do is evaporating some of this pheromone, which means we decrease these values, okay? Uniformly. And then each one of these uns, they leave something, they add something to the pheromone value of the link they have traversed, okay? And what they leave is 1 over the link length, okay? So this means the ones who traverse the link with length 1, they leave more, they add more to the pheromone value of their link than the other ones that have chosen the short path. They only leave 1 over 2, okay? If we simulate that, if we run that, and these are averages over 100 runs, okay? This is what's happening. So the difference between these two pictures is that here I have 10 uns and here I have 100 uns at each iteration. So we see first that, so this is the probability here, or the percentage of uns using the shortest path. So if this goes to 1, then the whole system has converged to the short path. Okay? So we see that in both cases they converge to the short path, but the variability here when I have only 10 uns is of course higher. Okay? In the extreme case, when I only choose 1 unt, it can even happen for decisions in the first iterations, because they are probabilistic, that the system will converge to the long path. Okay? But the more unts I use per iteration, the more I can be sure that this converges really to the short path. Okay? And this is an optimization capability, which is, if you want to express that in biological terms, due to cooperation. Okay? But of course, there are some differences between the reality and our model. Okay, so in real unts, they are not walking goal-directed. They are walking also asynchronously. They're not all moving at the same time from one place to the other place. Okay? In our simulated ants, we do that in a synchronized way. Okay? Pheromone laying. So real ants do that while moving, and the determining factor is simply the time they need. So when they traverse the short link, they arrive first at the goal, okay? Earlier at the goal than the ones who walk along the long path, okay? Here we have to simulate that in our model by different quantities they add to the pheromone values, okay? The ones who traverse the short path, they add more quantity to the pheromone value of their path than the ones who traverse the long path, okay? But still, this model models what happens really in reality, okay? But what's the problem with this model? I mean, we want to do optimization, right, with that. So what are we doing? How many solutions do we have in this? If you see there's an optimization problem, we have two solutions, right? Short path, long path. And we have pheromone values on solutions. We cannot do the same. We cannot take that and transfer it and have directly an algorithm for optimization. Because if I need a pheromone value for all the solutions, I have solved my problem and there's no need to do further optimization, right? So there's another difference, let's say, to the final technical algorithm, which is ant colony optimization. The difference is that these pheromones, they are not on solutions, they are on solution components or parts of solutions, okay? So this is the final meta-heuristic, let's say, okay? The general working of the meta-heuristic. Here we have a problem to be solved, a discrete combinatorial problem to be solved. And first of all, I have to define what are my solution components. Okay, this is different for all problems. If I have a subset problem like knapsack, then the items are my components. Okay, but also for the same problem, there are different ways of defining what the components are. Okay, usually when you have a greedy heuristic, this gives you a good idea. You have different greedy heuristics for the same problem, for example, and all these greedy heuristics, or they might use different solution components, okay? So if you have a problem and you want to solve it with ACO, it's a good idea first to look at greedy heuristics which are out there for this problem. And this will give you an idea of what the solution components will be for you and for your ant colony algorithm, okay? Usually what we do is we generate then one pheromone value per solution component. This is the very usual way, but there are also other systems which have been studied. But I would say in 99% of the cases, this is what's done, okay? So one value per solution component. And then we have an iterative algorithm, okay? So the first step of each iteration consists in probabilistically constructing a number of solutions, okay? And this is done by the mechanism of a greedy heuristic, but we are not doing that greedily. We are doing that with probabilities, okay? We are executing the greedy heuristic, if you want, in a probabilistic way. And these probabilities, they depend on the pheromone values. They are calculated on the basis of the pheromone values, and if you want, and this is most of the times done, based on the greedy information, okay? So a combination of pheromone information and greedy information. So we construct a number of solutions, and then these solutions, or some of these solutions, even solutions from earlier iterations, are used for making an update of these pheromone values, okay? And what we are doing is we are using generally good solutions, okay, for doing this pheromone update. And the idea behind this is that after time, the more time passes, the construction of solutions will move to areas of the search space where I find better and better solutions. Okay, because what we do here is with the pheromone values and our greedy mechanism for generating solutions, we have a probability model, a probabilistic model. Okay, and we sample this model in order to get solutions. And then with these solutions, we change the values of the probabilistic model, okay, with the aim of guiding or making it more and more probable at each iteration to construct better and better solutions. That's the idea behind. It doesn't always work. Okay, so people were checking situations, studying situations where this does not work. Okay, but generally it works. Okay. So this is the whole thing in terms of pseudocode. Okay. So we initial the pheromone values to the same positive constant, and while we have still computation time available, at each iteration we construct a number of NA solutions. Most of the times we apply also some local search technique, okay? So some, or let's say it more in general, some technique for improving the solutions that were generated. And then we apply a pheromone update, which depends on this set here and on earlier solutions from earlier iterations, okay? So just to put that into a timeline, I would say it's a fact. Uncolonial optimization is one of the rather early metaheuristics, okay? And so the first ones were simulate annealing and tabu search, okay? Then we had genetic algorithms for combinatorial optimization. So you find evolutionary algorithms which are much older, but they were not generally for combinatorial problems. Then uncolonial optimization, and then you have a whole lot of other ones. I will tell you later also that this stops basically at year 2000. So after that, I would say you have no essentially new idea, new metaheuristic, okay? And this also relates to what we were saying this morning. Of course, there are people who propose seemingly new metaheuristics with sometimes funny names like flying elephants, so this was no joke, this really exists, okay? Or penguins, whatever, okay? But I would say since the year 2000, more or less, there was no really essentially new idea. And then this is when people started to do some hybrids, okay? They started hybridizing different metaheuristics, but then later also what you have seen already examples, hybridizing metaheuristics with exact techniques, for example, okay? So, but let's see a small example still, okay? I will do one of these examples and then we will go towards hybrids. Let's have a look at the Tsp example because it's the simplest one. So let's solve this Tsp problem here on 4 nodes, okay? Of course, there are 3 different solutions, okay? So this one here of function value 8, this one here function value 10, and this one here has value 10 as well. So this is the optimal solution, okay? So I explained it on this example, but of course this is general. So first of all, if we want to solve that with uncolonial optimization, what we do, what I said before, we have to say what are our solution components and what is our pheromone model. So where are my pheromone values? And in this case, the components are simply the edges of the graph, okay? So each edge corresponds to a solution component. And moreover, we have for each of these solution components a pheromone parameter with its value, okay? So on each edge, we have one of these pheromone parameters with its value. Now, let's say we construct solutions step by step, okay? For convenience reasons, we start always in city 1, and then we add one city at a time until we have a Hamiltonian cycle, okay? And we do that in a probabilistic way, okay? So in the first step here, we are here, and we can add any of these other 3 nodes, and the probability to take this edge here, so to go to node number 2, is calculated as the pheromone value of this option divided by the sum of these 3 pheromone values, okay? And in the same way, you calculate the probability for the other 2 options here, okay? This is now without using any greedy information, but you could couple this pheromone information with greedy information, for example, simply multiplying it, and then producing the probabilities in the same way, okay? So let's say for probabilistic reasons, we went to 2, and then we do the same again. Okay, so the probability to choose this link here is this pheromone value divided by the sum of these two. Okay, the probability to go here is this pheromone value divided by the sum of these two. For probabilistic reasons, let's say we went to 4, and then we have to go to 3 and back to 1. Okay, so this is our way of using these pheromone values in order to generate solutions. Now, after generating solutions, we also need an update. Okay, and the earliest update that was proposed is this one. Okay, so first of all, we do an evaporation, and then we add something. Okay, this is the term we add to each pheromone value. And what we do is, for each solution in the set of solutions that were generated in the current iteration, we take these ones that have the corresponding solution component, okay, that include the edge that corresponds to this pheromone value, and for these solutions, we add a quality term. Okay, and this quality term is, in this case, because we minimize 1 over the objective function value. Okay, this means that solutions that are better contribute more to the pheromone update. Okay, and this is what happens. Okay, so let's say in iteration 1, okay, this is the thickness of the lines here shows you the pheromone concentration. Okay, at the beginning it's initialized to the same value, so the lines have all the same thickness. Then we generate, let's say, 2 solutions in the first iteration. Let's say these are these 2. Okay, this one has objective function value 8, and this one 10. Okay, so all the pheromone values here on these 4 edges, they will receive as a reinforcement 1 over 8. Okay, and all the edges in here, the pheromone values on these edges, they will receive as a reinforcement 1 over 10. Okay, because the objective function value of this solution is 10. And this changes my pheromone concentration, okay, which in turn changes the probabilities for constructing solutions in the next iteration. Okay, and if we leave that going, we will converge to a solution, to a specific solution. Okay, then at some point we will have only, at each iteration, we will have only one solution, always the same, over and over again constructed. Okay, so this is basically how the algorithm works. Okay, do you have any question about that? Or was that clear? Anyone, any doubts about the general idea of this metaheuristic? No. Okay. So I would say then we move towards hybrid. Okay. No. Yeah, well, yes. Let's talk about this hybrid first. This is about a hybrid which I call BeamArco. This was coming from our own work. It's already quite a bit older, but it's still used. So this combines a tree search technique, which is called beam search, with uncolony optimization. So the idea is as follows. Beam search is a tree search technique that limits the number of partial solutions that I can look at or consider at each level of the search tree. Okay, so if you recognize that, this is the search tree for our Tsp example. Okay, we start in city 1, then we can go to 2, 3, or 4, and so on. Okay, so the path down this search tree is solution construction. Okay. Now, beam search would tackle this problem as follows. Okay, so we need 2 parameters for this version of beam search. There are different versions, but we use this one. This first kx parameter tells me how many extensions. How's that? 3. How many extensions can I take from each partial solution? Okay? The other one is how many partial solutions can I keep at each level of the search tree. Okay? So in the first step, I have these three possibilities, and I take the two best ones. Okay? Because this kx parameter tells me you can take the two best ones. So at this level of the search tree, I have two partial solutions, and there's no problem yet because I'm allowed to have three. So in the next step, I extend this partial solution, I extend this partial solution in two possible ways, because in this case, there's just two ways. And now I have a problem because I have four partial solutions, and I'm only allowed to keep three. Okay? Now I use a lower bound. Okay? This is a different way of evaluating partial solutions. I use a lower bound to evaluate these four solutions, and I take the three best ones according to their lower bound values. This is what beam search is doing. Okay? So in this case, we would exclude one. In this case, it's just exemplary. We excluded this one. Let's say this one had the worst lower bound value, and we are finished. Okay? But in principle, this would be done by beam search in each step of the construction process. Okay? Now, uncollinear optimization is also a tree search algorithm, if you want, because it's based on solution construction. Okay? And each constructive mechanism can be shown in terms of, explained in terms of a tree search. Okay? So in this algorithm, what we do in BeamAcco is, instead of having NA independent solution constructions per iteration, because even though they are probabilistic, they are independent usually in uncollinear optimization, what we do is we perform a probabilistic beam search based on pheromone values and greedy information with a beam width. Okay, so this is the number of partial solutions I can keep at each level, with a beam width equal to the number of solutions that I want to construct. Okay, and now these solution constructions, even though they are probabilistic, they are interdependent. Okay, and there's another guidance mechanism which is used by this algorithm, which is the lower bound, which is rarely used, let's say, in constructive techniques. You find examples, of course, but generally you don't use lower bounds. So these are the advantages: strong guidance, additional guidance by the lower bound, and it's embedded in the adaptive framework of uncollinear optimization. So it will not do the same at each iteration because your probability model changes. Okay? So if you want, you can call uncollinear optimization, or, well, in general, uncollinear optimization, not just BeamAcco, an adaptive probabilistic greedy algorithm. Okay? And here you have this additional feature of the guidance by the lower bound. So this has shown really good performance in some problems, especially scheduling here, the traveling salesman problem with time windows. So at that time, this was really the best algorithm. I think since then another one was coming out. This is always the game, right? You improve something, and then it's just a matter of time until someone else comes and has even a better idea. But at this time, this was the best algorithm. Okay. Also for things like vehicle routing, this has been used. Okay. So now let's talk about two other hybrids. Okay. And before starting with this part, I want to say, until now, and also for the rest of the talk, you have not heard me pronouncing the term company or business. Okay, so this differentiates me maybe from the speakers we had before. This is simply because I think my type of research is more basic. Okay, it's not so applied. It's more basic, what we are trying often, we also apply things, but rather to academic problems. But what we try is to have algorithmic advances. Okay, so the development of new general algorithms that can later then be useful in applications. Okay, to real problems. And the applications that we do, they are generally there in order to show that our algorithms work. Okay, so that there is some use of this for these algorithms. And what we are doing generally is using exact techniques, but not specialized exact techniques, we have a different approach. We use black box solvers, okay, like Cplex. Yesterday we had someone here from Cplex, from IBM. He was talking about Cplex, CP optimizer, and so on. There are other options like Gurobi and how they are called. Okay, so there are different CP engines, different MIP solvers. And our approach is like that. How can we use these black box tools in a better way than just applying them with their default values to a model that we have? Okay, is there a better way of using these tools? And so especially our own work about construct, merge, solve, and adapt, this algorithm which I present last, is based on this idea. Okay, but also the next one, which is not our work, which is simply one of the best known algorithms we know from this field. Most general algorithms you find in this field, large neighborhood search. Okay, but first of all, well, I talked about this already. I want to give you a short 3 slides introduction into this field. So what is a hybrid metaheuristic? Or math heuristic, no? We heard this term this morning, math heuristic. Well, math heuristics are better defined, let's say. A hybrid metaheuristic is even more fuzzy what it is, okay? The problem, if you want, is that it cannot be very well defined, okay? For example, an optimization algorithm which uses local search internally, is this already a hybrid technique? You might call it a hybrid technique. For me, it's not an especially interesting hybrid, okay? When I'm thinking about hybrids, I think about combining algorithms from different areas of optimization, okay? So it's a technique that results from the combination of methods with other techniques for optimization. And here we have like branch and bound, dynamic programming, ILP techniques, like, okay, column generation or whatever. So this lack of precise definition I've encountered that sometimes, because we started in 2004 with a workshop which is called like that, hybrid metaheuristics. And when I went to other conferences, people said sometimes, yeah, but this, you cannot even define what it is, okay? But for me, this is not a problem. If you define something too well, you also close, let's say, the frontiers to other techniques, and you are closing yourself in, okay? So for me, this is not really a problem. The reason why we talk about hybridization is this one. So even in metaheuristics, the different communities like evolutionary algorithm community, you know, local search community, or even within local search, like the BNS people, the ILS people, the Tabu search people, for some time they were quite isolated from each other. They didn't look too much what the others were doing. Okay, this is because they wanted to sell their product, basically. Okay, this is also very understandable, and tried to push that. So they didn't look very much what the others were doing. But as I said, since the year 2000, there was no really new idea. So people started to think about what the others were doing and how to best combine these kind of things. Okay, and then you see these workshops and conferences coming up. Like the first one was CPAIOR. I don't know if some of you know this conference. This is about tries to combine constrained programming, artificial intelligence, and operations research. So a very broad field. So if you go there and you send something like which is completely OR, they will not accept it because they require a combination of things. Okay. And then you have our workshop from 2004 and the math heuristics workshop. There's also a specialized workshop on math heuristics, which is started in 2006. Okay. This is a bit of general literature, so if you're interested in that, you can see that in the slides when you download them from the page. Okay. Now let's start with large neighborhood search. Okay, so when you do neighborhood search, what you can do, well, first of all, you have to define what the neighborhood of a solution is. Okay, so you have to define your neighborhood. You have to choose your neighborhood. And what you can do is using a small neighborhood. Okay, so you can define a neighborhood such that each solution in the solution space has only very few neighbors. Or you can choose a neighborhood which is much larger. Okay, so where each solution has a really large subspace of neighbors. And of course, both has advantages and disadvantages. Okay, so the advantage of small neighborhoods is, of course, that it is fast to find an improving neighbor if your current solution has any. Okay, the disadvantage is that the average quality of the local minima is quite low. When you have large-scale neighborhoods or large neighborhoods, then the advantage is that the average quality of the local minima is rather high. You have also much less local minima. But the disadvantage is that finding an improving neighbor sometimes is also an NP hard problem. Okay, or let's say in general, a very, very difficult problem. So how can you examine these large neighborhoods if you decide for that? Either heuristically, okay, you generate solutions one by one in this neighborhood in a heuristic way, and once you find the better one, you take it. Or in some cases, you can find an efficient exact technique that gives you the best neighbor or simply a better neighbor than the current solution that you have. Okay? And this is, well, there are many different ways of generating large neighborhoods. Okay? This goes more towards the direction of, let's say, MIP-based large neighborhoods, okay? Destruction-based large neighborhoods. So we generate an initial solution, then in each iteration of the algorithm, we destroy this solution partially, okay? So this gives us a partial solution. Then we apply an exact solver. This might be an ILP solver if we have an ILP model for our problem. Telling this solver, in addition to the model, that it must contain this partial solution. Any solution it gives me must contain this partial solution. Okay? This gives me the best solution I can find if I have the time to solve this model to optimality. This gives me the best solution in the search space that contains this partial solution. Okay? And then I choose between my current solution and the new solution that I got here to be the current solution of the next step. Okay, the most simple decision is simply to take the better one of the two, but it's not always the case that this is the best decision. Okay, but this is the simple mechanism of a destruction-based large neighborhood search. So in this way, even if we have a problem instance that cannot be solved by or even tackled by as a complete instance by the solver, okay? So sometimes the model might be even too large to fit into memory, okay? So with a mechanism like this, like large neighborhood search, we can apply this model to a reduced search space, okay? So even if we might not be able to tackle the initial problem, the complete problem, we might still be able to apply our solver to the reduced search space. And then it might still be useful to use it in this way in the context of large neighborhood search. Okay. So let's have a look at this example. Okay, I have enough time. So this is a very an NP hard problem, but a very simple to explain and to state problem. Okay, it's called minimum weight dominating set. So most of you, I guess, will know this problem. We have an undirected graph where each node has a positive or zero weight, okay? A positive weight, let's say. Valid solutions are subsets of the nodes such that each node in the graph is either in this set or has at least one neighbor in this set, okay? So all the nodes in my graph, a solution S, which is a subset of all the nodes, is a valid solution if each node in the graph is either in this set or has at least one neighbor in this set. Okay, then this set is called a dominating set. Okay, and the objective function value of such a valid solution is simply the sum of the weights of its nodes. Okay. So here we have an example. Okay, so this is the graph. These are the node weights here. This is a valid solution here. So only this node, because all the other nodes are neighbors of this node. Okay, so it's a valid solution. Has function value 4, but the best solution here is the combination of this node with this node, all the other nodes have them as neighbors, and the sum of the weights is 2. Okay? So we are looking for a valid solution which minimizes the sum of node weights. Well, for this problem, the ILP model is very simple. Okay? We have a binary variable xi for each node vi. This here is the closed neighborhood of node vi. A closed neighborhood means these are all the neighbors and the node itself. This is the closed neighborhood. Okay? So we say that for each node, the sum of the binary variables of all the nodes in the closed neighborhood must be greater or equal than 1. So this means if the node itself is in the set, then this is 1. This sum would be 1, at least 1, because maybe some of its neighbors is also in the set. Okay? But we forbid that this sum is 0, because this means that the node is not in the set and has no neighbor in the set. Okay? So this sum must be at least 1. That's it. Objective function value is summing the weights of all the chosen nodes. Okay? So in our large neighborhood search, when we have a partial solution, which is obtained by when I have a solution, a valid solution, I take away some of the nodes. Okay, partial destruction. Then I get so a partial solution is a set of nodes again. Okay. In order to tell the solver that this partial solution should be in any valid solution, I simply say all binary variables of nodes that are in this set are preset to 1, must be set to 1. Okay? This forces the solver to have this partial solution in any valid solution. And then we need well, a greedy algorithm, let's say, or any other technique for generating the initial solution. Okay? So in this case, there's a quite simple greedy algorithm which starts with the empty set. Okay? And then it adds, at each step, it adds one node to the solution until I have a dominating set. And then I stop. Okay? And for this greedy algorithm, well, you need these two definitions. So this VCOV is the set of covered nodes with respect to a partial solution. This will be all the nodes in the set and neighboring to this set. Okay? And the current degree of a node which is not yet in the set is only considering the covered nodes. Okay? So, for example, here we have a partial solution which contains node V1 and V7. Okay, it's a partial solution because this node, for example, is not covered yet. Okay, has no neighbor. It's not in the set and has no neighbor in the set. Okay, so for example, the current degree of this node is not 3. Okay, it's just 1 because this node is already covered and this node is already covered. Okay. So with this definition, we start the greedy algorithm with the empty set. At each step, while I have not a valid solution, I choose the node of those nodes that are not yet in the set that maximize this value here, which is the current degree divided by the weight. So, of course, we prefer nodes that have a large degree, large current degree, which are covering many nodes, and which have a small weight. Okay? So we are using this algorithm for generating the initial solution, and then the standard method for destruction, which we are also using here, is we have a percentage here of the nodes that we will remove. Okay? And the simplest way of removing nodes from a solution is randomly choosing them. Okay? I will not go into the other option because you might have also greedily biased selections. Okay? This is an idea which you also find in variable neighborhood search, which we saw this morning. So what we do is we start with a small percentage. Okay, so we try to remove just a few nodes from the current solution. In this way, the ILP model is much quicker to be solved. Okay, so if we can find better solutions in this way, we keep the percentage small. But if this is not possible, we will increase, and this is what we used. This is just an example, okay? This is not a published paper, nothing. I implemented that as an example. So if we don't find an improving solution in this way, then we will increase this percentage until a maximum. And when we reach this maximum, we go back to the minimum percentage, okay? This is like in same mechanism as in variable neighborhood search. Okay, so let's see some results, okay, because they are characteristic for this type of this type of algorithm. So you have graphs of different sizes, okay. These are the number of nodes with different densities, and let's have a look at some results. So this is for low density graphs, medium density graphs, high density graphs, and here you see the improvement of LNS over greedy. Okay, first we can compare to greedy. And this is in percent here, okay, so for different graph sizes. And we see that for small graphs we are usually have a higher improvement over greedy, which is going down a bit when we go to larger graphs, okay. This is a phenomenon which you find very often, that greedy algorithms in relation get better when the problem gets bigger. Now, let's compare to CPLEX, okay? Applying CPLEX directly to the original model. So this is the improvement of LNS over CPLEX. And of course, if this improvement is positive here, then we have an improvement. Later you will see negative values also in another example. This means that the other one was actually better, okay? But here we have everywhere improvements over CPLEX. This is actually something we would like to see. When we have small instances here, then we get the same results as CPLEX, because CPLEX solves these problems to optimality, and we want, actually, at least we don't want to be much worse with our large neighborhood search algorithm than CPLEX when it can solve the problem to optimality, okay? So this is what happens here. But when we go to bigger graphs here, we see that we get more and more improvements over CPLEX, because when the problem size is growing, CPLEX has more and more problems to solve these instances, okay? So this is very characteristic, this curve. At the beginning, we get the same results as CPLEX. When we go to bigger graphs, we get improvements. Now let's have a look at this other complementary algorithm, let's say, that we developed. So, and the development of this algorithm is based on basically this observation. So LNS, in our experience, tends to work well when the number of solution components is not too high. Okay, in solutions, sorry. No, the other way around. So when the number of solution components in general is not too high, in your problem, and the number of components in the solution is not too small. So what does that mean? When I have a problem, let's say for very sparse graphs, if we think about this minimum weight dominating set, if I have a sparse graph, solutions will be bigger, okay? Because it will need more nodes to cover all the nodes of the graph. If I have a very dense graph, in the extreme case, if I have a completely connected graph, any node is a dominating set because it's connected to all the other nodes, okay? So the more sparse the graph is, the bigger the solutions will be, okay? And what we say here is that in our experience, LNX works well for those type of instances, let's say. You can also look at this at instance level, not only at problem level, when the number of solution components in a solution is not too small. So the solutions are big. On the other side, when solutions are small, LNS doesn't work often so well because you might have long paths jumping from solution to solution until you reach a really good solution from your current solution, okay? While when solutions are big, then your current solution might have already some part in common with really good solutions, okay? So this is the reason basically behind. So what can we do when this is not the case? So when we have small solutions, instances or problems with small solutions. And we thought about this general mechanism, okay? So observation is that in the presence of a large number of solution components, many of them only lead to bad solutions, Okay, so can we exclude presumably bad solutions, solution components, from the ILP before solving it? Okay, if we know that if you have an ILP, okay, and you know that a certain setting of a variable will not give you a good solution, then you can reduce this domain of this variable before solving the problem. Okay? If you can do that very often, then you have a problem at the end which is much reduced, and CPLEX might be efficient at the end or a MIP solver efficient at the end in solving this problem. Okay? So this is the idea. And the steps of the method are as follows. So we iteratively generate presumably good solutions in a probabilistic way, like in ACO, okay? Just without pheromones and without learning components. Then we assemble sub-instances to the original problem instances from these solution components that I find in these solutions. Then I solve this sub-instance with the ILP solver, for example, or any other exact technique. Okay. And then, as a last step of each iteration, we delete seemingly useless solution components that are in my sub-instance that I have added at some point. Okay. And this is the final algorithm. Okay. So C is the complete set of solution components. In our TSP case, this would be all the edges. Okay. In a more general MIP context, a component would be a variable value combination. Okay, so all variable value combinations is my set of solution components. C prime is always my sub-instance. This is a subset of all the solution components. Okay, at the beginning, so all the solution components have an age. This is one of the parameters, or one of the mechanisms of the algorithm, and this age is initialized to 0. Then at each iteration, what I do is first I probabilistically generate NA solutions. Okay, say C hat is the set of solution components that I find in these solutions. Okay. Then I add all these solution components that are in C hat and not yet in C prime. I add them to C prime, to my sub-instance, which is initially empty. And I apply an exact solver to this sub-instance, which is a reduced model. Then I increment the age of all the components in C prime. Okay, when they enter C prime, their age is 0. Okay, so at this point, I increment the age, and I set the age of all components in the best solution to my sub-instance. I set these ages to 0. Okay, so imagine in the TSP case. Okay, I generate solutions. Then I add all these edges of these solutions to my sub-instance. Then I solve the sub-instance only based on these edges. This gives me a best solution in this sub-instance, right? Then the age of these components is put back to 0, and the age of all the other components in my sub-instance is increased. Okay? And in the last step, what I do is I remove from C prime all those components that have reached a maximum age. How can a component reach a maximum age? When it never appears in the best solution to the sub-instance. Okay? So these are then, after some while, okay, on age max iterations. If in age max iterations a component has not been in the best solution to the sub-instance, I kick it out. Okay? It's a very crude criterion. But, and this is probably one of the aspects where you can improve this algorithm, okay? But at the moment, this is what we are doing. If you want to compare the two algorithms, okay, both are based on applying an exact solver or MIP solver to reduced sub-instances. In one case, in the LNS case, large neighborhood search case, this subspace is defined on the basis of a partial solution. The subspace is the set of all solutions that contain this partial solution. In the other case, in CMSA, the subspace of solutions that are in my sub-instance are those solutions that are exclusively composed of components from C prime. Okay? So in both techniques, I produce sub-instance, but in different ways. Okay, let's see. I have two examples, and I'm just thinking about which one is the easier one to understand. Okay, let's have a quick look into this one. This is for a problem, and now I see that I've made a mistake because this morning, actually, I changed the outline of this talk this morning when I decided to put colony optimization in there. And I see now that I have removed the definition of this problem. Okay, but I try to explain it in words. Okay, it's quite easy to be explained. So this problem is called repetition-free longest common subsequence problem. Okay, when you have a string, any subsequence of this string can be produced by deleting letters from this string. Okay. So a subsequence of a string is a sequence of characters that appear in this order in my input string, but not necessarily in a consecutive way. Okay? So also the empty string is a subsequence of an input string if I delete all the letters. Okay? Now, when I have two input strings, I can ask for the sequence which is the longest common subsequence, the longest subsequence of both input strings. Okay? So a string that I can produce from both input strings by deleting certain characters. Okay? And I want to find the longest string that I can produce in this way. This is the longest common subsequence of two input strings. Okay? Now this problem has an additional constraint, let's say. The constraint is that in a solution, in a subsequence, a solution can have each character at most once. Okay? This is an additional constraint. This problem, even for two input strings, is NP hard. It's APX hard, which implies that it's NP hard. Okay, so what do we need in order to apply CMSA? We need a constructive mechanism for probabilistically generating solutions, and we need, if we have one, an ILP model, for example, or a model for solving this with CP or whatever. Okay? In this case, we used an ILP model. But first of all, let's have a look at the greedy heuristic. Okay? So we start. This again builds a solution step by step. Okay, so a substring of input strings x and y, step by step. And at the beginning, this t is empty. Okay, it's the empty string, and we add character by character in order to construct a complete solution. Now, this is the set of allowed characters at each step in order to have valid solutions. And the question is, how do we do this choose from? Okay, how do we choose one of these characters at each step? Okay, this can be explained with this example. Let's say we have this input, this instance here. Okay, so we have two input strings, x and y. These are these two strings, and they are DNA strings, let's say. Okay, they don't have to have necessarily the same length. This is simply, well, I did it like this. Okay, but it's not necessary. And let's say this is our partial solution, okay, AC. And of course, AC is a subsequence of this one because we find AC here, okay? And it's a subsequence of this one, AC, okay? Now, such a partial solution divides both input strings in a well-defined way into two parts, okay? Into the part which is processed already, okay? And into the part which is not processed. So this is processed because we look for the first A and then for the first C, and this is where we are. Okay, this is processed. We cannot take any more letters from this part. And the same for the second input string. For having AC, we look for the first A, then for the first C, and this is where we are. Okay, so now for extending the solution, we can only take letters from these remaining parts. These are the pointers to the next positions of the letters which are not yet in my solution. Okay? So this is the first T in the remaining part of the first input string. This is the first G here in the remaining part of the first input string. And the same for the second input string. Okay? So now I have, well, in general, I would have to decide between T and G. Which one do I choose? But in this case, it doesn't make sense, surely, to take a G, because in both cases, the first T comes before the first G. Okay? So if I take the G now, I could destroy a good solution, okay, which does not contain T at the end. Okay? It's not the case in this example, but it could be the case. Okay? This is what I call, so this set of letters which is what I call the non-dominated letters. Okay? T is not dominated, G is dominated. Okay? In general, in this set, I have the set of non-dominated letters that I can add to my current solution. Okay? And this is the greedy function. Let's not go into that. This is simply the greedy function of how to decide which letter to choose from the allowed letters. Okay? Now we have a greedy algorithm, and we can use that in a probabilistic way, okay, for generating solutions. And now we need an ILP model. Okay? And the standard model for this type of problem is as follows. So for each position I in the first input string and each position j in the second input string, such that I have the same character on these two positions, I introduce a binary variable. Okay? And I call it set yg. So here, every line here is a binary variable in the model. Okay? So here I have an A and here I have an A. So these two together build the binary variable. Okay? Here I have a T and here I have a T, so I have a binary variable between them. Okay? Now what I have to choose basically is a maximal set of lines here that do not cross. Okay? In graphical terms, this is my problem. And so something like this would be a conflict. Okay? And this is the whole thing in terms of an ILP model. Okay? So I have my whole set of binary variables. I maximize over the sum of them. And I say that for each two variables that are in conflict, whose line would cross, I can at most take one. Okay? And in this problem, I have also this additional constraint here, which says every letter can at most appear once in my solution. Okay? Okay, now let's see some results. Okay? And again, I've chosen this problem because you have the characteristic graphics, okay, which you would expect for this type of algorithm. So we have problem instances of different sizes. Okay, it's not so important. This again is the improvement of the CMSA algorithm in this case over Cplex, okay, for different sizes and different instances of different alphabet sizes and so on. So in this case, we get the same solutions as Cplex, and then there are no bars because Cplex is not able to produce solutions in the given computation time. So the improvement is infinite, if you want. Okay. Now, if we go to different instances of different characteristics, we have again this characteristic picture. Okay, we get the same solutions as Cplex for small instances, and then we get increasing improvements. And here, for these sizes, Cplex is not able to provide any feasible solution. Okay, and there's some more graphics for that. For different types of instances. I don't think we have to go into this. I just want to talk about one last slide. Well, no, this is an interesting slide also. What we do usually, we have large instance sets of instances with different characteristics. Okay, small instances, large instances, and so on. And we use a tuning tool. In our case, we use iRace. Okay, a tuning tool is a tool for setting the parameters of your algorithm, the parameter values, which gives us the best setting, if you want, for different categories of instances. Okay, and then you can study, for example, things like the size of the sub-instances, the average size of the sub-instances considered in your algorithm for different sizes of instance sizes. Okay? So here we have a growing alphabet size, growing instance size. so growing model size, if you want. At the beginning, you see, basically this means here, it doesn't matter. The problem is so easy that IIIA has produced any setting for the parameters, and the algorithm was able to solve the problem, okay? But then we see, starting from here, we see this slope, okay? And this is, this makes sense. So the size of the sub-instances, this is in percent of the original, okay? So for this instance size, our sub-instances are 70% of the original problem instance, so still quite large. But when we go to really big instances, this is about 10%, okay? So the sub-instances only contain about 10% in this case of all the variables of the original model, okay? And this makes sense because when the problem grows, when the model grows, in order for CPLEX still to be able to be useful, your sub-instances have to be every time smaller, okay? Okay, let's go to the last slide now. Okay. So an important part of our current work is the idea, or is the aim, let's say, to find a way of using CPLEX or a MIP solver in a better way by not having to use problem-specific information, okay? Because in this CMSA example that I've shown you, we have a greedy algorithm. We know which problem that is. We can design a specific greedy algorithm which helps us to produce relatively good solutions, and this helps us to assemble relatively good sub-instances. But what happens if someone gives you an ILP model and you don't even know what problem that is, okay? And you want to find a way of using CPLEX in a much better way, much more efficient way than just applying it to the original problem instance, okay? So I cannot explain to you details, I just give you this graphic because we have really, really good results in that. But this is not published yet, so I don't yet explain you exactly how this works, okay? So we found a way of generating sub-instances, also in a probabilistic way, not knowing anything about the problem, okay? And then we have here, this is for one of the binary ILPs, in this case, from MIPLib, okay? And we know this is the optimum of this instance. This is the behavior of CPLEX, of default CPLEX, okay, of the newest version of CPLEX. So it will give you better and better solutions, okay, over time. And these are the 5 runs of our algorithm, okay, because it's stochastic, okay. So I show you here 5 runs. And you see that at the beginning already we have a large advantage over CPLEX, and even in the final solutions found in this time frame, at least 1,000 seconds, okay, we are better than CPLEX. And this is more or less a general picture, okay? So this doesn't work for all the instances, but for many, okay? And I think this is this can be a nice addition to the literature. If you have a general method for improving over CPLEX, given simply some ILP model, this can be very useful, I think. Okay, but we first have to publish that. Maybe the reviewers tell us for some reason it's not useful at all. Who knows? Okay, but I think these are really promising results. Okay, so if you want to know more about these kind of things, hybrids especially, there are these 2 journal papers. This one is especially about construct, merge, solve, and adapt. And with a good colleague and friend of mine in Vienna, Günther Reidel, we have published this book on hybrids in 2016. Okay, thanks. Any questions?
Thank you very much for your nice presentation. It's a crazy question, but all the time was interesting about the idea was behind the particle swarm optimization and ant colony. But I want to know why you choose this difficult solutions method in comparison with other solution method metaheuristics such as ELS or VND. You know, it has more parameters, a little more difficult to implementation. You have to tune some parameters. It's my next question, how you tune the parameters that you use, for example, number of population that you generate for initial solution. I think for pheromone and probability, you need some parameters. Yeah.
And the first answer to the question is a very simple one, because when I started my PhD in 2001, it was with big data of uncorrelated optimization. So
Results. You know, I see some papers that they have high effort to tuning these parameters, and other ones just in one sentence that they mentioned, we use the literature review and we choose this value for these parameters. You know, it could be a bit.
Some operations research, I checked all these papers. No, I think you have to use an automatic tuning tool or to do a full factorial design.
Analyzing with ANWA.
You can do a full factorial design
Yeah.
if you have the computing power to do that.
Yeah, I do that for my thesis, 3 months tuning just parameters. Okay, thank you.
More questions? More questions?
Thank you so much, Christian, for the nice talk. And you mentioned something that you work in algorithms, not so much in business applications and things. But I would like to comment a lot on this, because I think your work and the work people are working in real problems are very complementary. One does not exist without the other. So people that work in real problems feeds and get knowledge from your work. And then we also propose new challenge problems for, challenge the knowledge up to that moment. So it's, for me, both of them, and I mentioned this in my talk, are very complementary, and we have to, to do one thing and the other, otherwise we'll be dead, all the groups. Yeah. So I think it's very good to have people that work on more developing algorithms. And this is a comment, and that is a question. Do you think we'll arrive to a point that I have a Cplex based on metaheuristics, that I could just plug the model and solve it? That's what you want to do it? That's what you want to do it.
Once this is published, I will approach IIIA.
The micro, because people in Riga is telling me that they cannot hear you.
Okay.
Thing is published, for sure I will approach IBM, such that they, or with our help, implement something like this plugged into Cplex already. Such that you can, such that you have a parameter in Cplex saying, use this way of using it. And I mean, this would be,
Breakthrough.
Yeah, I think so.
More questions? Good. I have a question myself. So you said, well, I have two questions, but I will go with one. You said that greedy algorithm gets better as the problem is larger, something like that. Can you elaborate a little bit more about that, because it's very interesting? So no more questions? So let's thank the speaker.
Bueno, pero me la beberé de aquí. Sí. Voy a cogerla yo. Well, the next speaker is Jessica de Armas. I am the one in charge of making her presentation, mainly because we are both from the Canary Islands, so this is my pleasure to introduce Jessica. That's the first reason, but the most important one is that we used to work together a couple of years ago, and she's a very hard worker person. She's very smart, and she will have a brilliant career in the next coming years. So just.
Thank you, Ben. Good afternoon, and since this is the last talk of the day, I promise to be brief. So what I want to do is try to talk about a hybridization of metaheuristics with machine learning for optimization with dynamic inputs. These dynamic inputs are the key for the application of this method that I'm going to explain. Okay? So the presentation is divided in 4 different parts. First of all, I'm going to explain why learning heuristic, what is the motivation behind this approach, what is important to know these kind of approaches. Then I go to explain some examples of application in order to better understand this kind of approaches. Finally, I will show you some figures, a numerical experiment, and some conclusions, okay? So let's start with the first part. Why learning heuristics? Well, during the last years, hybrid approaches has been extensively employed due to their success, as explained Christian Blum before. And this is because of their success dealing with realistic problems, okay? So, among other things. We have hybrid metaheuristics, as explained Christian, combining different metaheuristics. We have metaheuristics, combining metaheuristic with mathematical programming. We have sim heuristic, as explained Angel this morning, metaheuristic with simulation. And at this step, what I want to explain is the use of heuristics with machine learning, or by extension, metaheuristic with machine learning. But in a specific case, which is when we have dynamic inputs, okay? They are deterministic, they are not stochastic, but they are going to vary according to the structure of the solution. When we are building the solution step by step, according to the structure and the characteristics of the solution, then these inputs are going to vary. So imagine that we have this problem. We have a set of heterogeneous radio access technologies, rate 1, 2, 3, and these radio access technologies give a pay-per-use service to some set of customers. Each customer has to be assigned to a rate, and each rate can serve a certain number of customers. And here, for example, we have the simplest scenario. Well, as it is a pay-per-use system, the idea is try to maximize the benefit of this service, the service of all the rates to the customers, okay? So we can imagine the simplest scenario, which is this one, where we have static inputs. So we can solve, we have deterministic demands. And we can solve it using mathematical programming or using heuristics or metaheuristics, depending on the size of the problem. Then we have another scenario. Here we have random inputs. In this case, we have demands that are not deterministic. They follow a particular probability distribution. And in this case, we can use, for example, semi-heuristics or, for example, fuzzy techniques, etc. But let's imagine this last example. We have dynamic inputs. Why? Imagine that depending on the structure of the solution, the assignment of customers to rates, these demands are going to vary. Why? For example, if a rate gives service to a big number of users, the quality of service that it could provide is lower than if it has a less number of customers. So if I offer you, as a customer, a low quality of service, you are going to demand less, okay? So depending on how I'm assigning each customer to the rates and how many customers are assigned to the rates, I'm going to demand more or less. So demands are going to be dynamics, okay? Well, if we search in Google Scholar, the number of works that we can we have in Google Scholar using the keys metaheuristics, machine learning, or both together, we can create a graphic like this, where we can see that during the last years, there have been an increase in the use of these techniques, okay? Of course, we can see a sharp increase in machine learning, but machine learning can be applied to other areas, not only combinatorial optimization, many other fields. So that's the reason why we can see this sharp increase. But if we made a zoom at this part of the graphic, we can see also an increase in the last, in using metaheuristics and using both techniques together. Well, the existing literature analyzing this hybridization with machine learning with metaheuristic can be divided into different groups. On the one hand, we have works where machine learning is employed to enhance metaheuristics. And on the other hand, we have the other case, works in which metaheuristics are used to improve the performance of machine learning techniques, okay? So here we can see in a visual graphic, we can see the number of works that we have using machine learning application, metaheuristic application, and we can see this, this area in the middle where we have these works that work with both techniques. On the one hand, we have metaheuristic improving machine learning techniques, for example, classification, regression, clustering, etc. This is not the part that I'm going to explain today. And on the other hand, we have this part, machine learning enhancing metaheuristic. Here is a point where we can classify learning heuristics, this approach that I'm going to explain. And usually the literature, the works that are in that point can be classified again into different categories. We have specifically located hybridizations, for example, for this parameter tuning, or for population management in population-based metaheuristics, or even for local search, for neighborhoods. On the other hand, we have global hybridizations. We can use machine learning to select the algorithm that perform better to solve a particular problem or a particular instance of a problem. Cooperative strategies, new type of metaheuristic, etc. So as I said before, linear heuristics are in this point, and if I have to classify, probably in this side. This is the framework. What we have is, we need a historical data on inputs here, a number of scenarios where I have the scenario and which inputs has this scenario. Then, with machine learning methods, I can create a predictive model, okay? And on the other side, I have my constructive heuristic. I have a problem, and I'm building my solution step by step. And at each step, I ask to the predictive model for updated inputs, according to the structure of the solution that I have until the moment, which are the updated inputs, okay? Then I perform the next step. And I do this loop once again until the solution is completed, okay? If I don't use these updated inputs, probably we are obtaining a suboptimal solution because we are just taking some inputs that are not updated, okay? So we can see this framework in another way. We can see as a pseudocode. Initially, we need to build the predictive model using this historical data. Then we have the empty solution, and we start a loop. Here we have the while loop, in which step by step we are iterating, for example, over a list of elements. In this case, in the example that I explained, the list of customers that I have to assign to each rate. So I iterate, I update the input before each step, and then I perform the next step. And finally, I can obtain the final solution, okay? There are some ways to extend this framework. For example, we can use more than one predictive model. We can use a combination of predictive model instead of one predictive model. We also can use an online approach in the sense that we can use the data that we have here to feedback the predictive model. That's all. That's the way that I can extend this framework. But the idea is that I can integrate this framework inside some meta-heuristic, simple meta-heuristic as grasp, as iterative local search, as this kind of easy meta-heuristic, okay, where we need a constructive heuristic inside. So instead of using the constructive heuristic, we use the learning heuristic, okay? The heuristic that learn about these dynamic inputs, okay? So let's see some example of application in order to better understand this approach. For example, transportation field. Here we can think about a vehicle routing problem or a routing problem where we have one depot or more than one depot and a set of customers that I have to serve, okay? We can think that the customer's demand may vary according to the position or the time or even the time window at which this customer is served. So depending on how I build the solution, these demands, the demands of these customers are going to change. Other parameters that can be dynamic, the traveling times. If I have two customers, the time between these two customers can be different depending on the particular hour of the day. If we have traffic jams, probably this time is larger than in other time of the day where there is no traffic jam. Okay? So this is an example of application. If we don't use updated inputs, we are overestimating most of these demands or traveling time. So the solution will be not so good. Okay? Other field, logistics. Here we can think about facility location problems or similar problems where we have some facilities. We have to choose the position of these facilities, and we have to decide which customers are assigned to each of these facilities. What's happened if, depending on the particular structure, the particular way in which I create the solution, the customer willingness to spend will be different. Therefore, the demand will be different. For example, imagine that a case. We have a supermarket, and I assign customers to these online shops or supermarkets or whatever. If I have, for example, an offer in that facility, and I assign this customer to this facility, I know that this customer is going to buy more things because there is an offer on this particular product. If I assign the customer to another facility that have not this offer, he or she is not going to consume that kind of product in the same way. But additionally, if I have too many customers assigned to this facility consuming that particular product, I can demand this product in a different way because the offer ends or this kind of things. This is just an example. So depending on the particular structure of the solution and how I'm assigning and opening the facilities, the demands change. So this is a case in logistics. In the production field, here we can think about scheduling problems. We have a set of tasks that we have to develop, of jobs, and we have processing times. And we can think that if we have, for example, we have machines and we have the jobs. If I assign a job later in the line, there could be more probabilities that this machine breaks or needs some update. So probably this time will be larger than if I put the same job at the beginning. Or if we talk about people, people that is developing these jobs, at the end of the day or the later in the day, more fatigue could have this person and need more time to develop a particular task. So depending on the particular time where we locate this job, we have different processing times. We can learn these times using historical data. And using that in a constructive heuristic that is locating these pieces of this job in the corresponding machines. In the finance, this is a completely different area. Here we have, for example, the portfolio optimization. The covariance metrics measure the risk associated with each pair of assets, and it could be a function of the current portfolio structure. How many other assets I have, how much I invest in each of these, in each of them, etc. And there are other management, risk management problems similar to this, where we have this kind of dynamic inputs, and linear heuristic could be useful. So now I'm going to show you a numerical example just to see the potential of this, this approach. And it's particularly the first case. For the transportation, we talk about vehicle routing problem. And we have the initial demand of each customer. This initial demand is an upper bound. Why is an upper bound? Because I have the demand if the customer is the first one to be served in the route. Imagine that is the first one. I know the demand if the customer is the first one in the route. If it's the second one, third one, etc., the customer is going to decrease the demand, okay? For example, if you serve, I'm a customer and you serve me early in the morning, probably I will demand you more things that late in the afternoon where I don't have the same needs. So I use that, if I use this initial demand as an upper bound, I'm overestimating the things that I need to put in my vehicles. So I will use more vehicles. I will need more distance, more cost, more time. So I will obtain a solution that is worse than in the case if we consider these dynamic inputs. In this particular case, for an illustrative purpose, we create this regression model. Here we have the demand, and the demand depends on some parameters. On the one hand, we have here the position. D0 is the initial demand, and I decrease the demand according to the position in which I serve the customer in the route. Well, using this simple regression model, imagine that we have this model because we have historical data and we have tuning the parameters. Then, if we don't use it, and we start from the initial problem, knowing the upper bounds, the initial demands, and I use, for example, the Clark and Wright heuristic, I can obtain this solution. In this solution, I have 100 customers and 11 routes, and almost 900 units of cost. Okay, this is the standard way. I solve the problem with my data, and it's what I obtain. And now I am going to use this approach, linear heuristics. I get to learn about the demands, and I got to create my routes according to these demands step by step. Each time that I perform a step, I update the inputs. And in this case, I obtain this solution. As you can see, we obtain just 8 routes, 3 routes less, and the cost is reduced almost 800 units. So you can see the idea. You can see that using these approaches, we are able to reduce our objective function. And this is just an example. As you can see, there are other fields of application. So conclusions. Real-life problems faced by companies are becoming increasingly complex? Yes. And as a consequence, hybrid approaches are good options. In this case, I present this particular application or combination of metaheuristics and machine learning. is for the particular case where inputs are dynamics, are not fixed in advance. They are going to change according to the structure of the solution that I'm building. And we are learning the relationship between the inputs and the solution characteristic using this historical data. Well, this is the reference of the work where we explain all details about this approach. I'm an author, but also Angel Juan, David Masip, and Laura Calvet. And well, that's all. I promise to be brief, and I will be brief.
Well, it's a very interesting topic. I'm very interested. I want to ask one thing about basically the termination criterion of the algorithms you propose. In the pseudocode, it said that until the solution is completely built, which I don't exactly understand what it is, but I'm wondering if there is some equilibrium involved in this. Because since the parameters vary according to your solution, does it often happen that at some point you reach some kind of equilibrium? For example, in the first example that you showed, where you could associate customers to some distribution, I don't know, some wireless thing, and the demand varied according to how many you associate to each antenna, let's say. So maybe at some point there is an optimal equilibrium of customers that can be assigned so that the average quality of service and the number of customers, so your revenue, are both, let's say, maximized at the same time.
Well, I don't know exactly to answer you. Well, regarding the stopping criteria, we are talking about constructive heuristic. So you are performing step by step. For example, in the vehicle routing problem, I have a depot. I'm including a customer. I check the updated inputs. Now I know the updated inputs, and I perform the next step. And which is the next step? It's the aggregation of a new customer to the route that I'm building, step by step. When I finish all the list of customers that I have to add to my solution. This is in terms of a vehicle routing problem. If I'm talking about the facility location, at each step, I decide which facility open and which customer I assign. Okay, so that's the same. So
this is when you finish building the greedy solution.
Yeah.
And then this is embedded into a meta-heuristic algorithm.
Oh yes.
For which instead you have a classical termination criterion. That could be number of iterations or time.
Well, you can use the framework that you want. It is a multi-star, but you can use a grass, an iterative local set, and use the stopping criteria belonging to that, to the particular meta-heuristic. The question is just, instead of using a constructive heuristic at some points, you use the learner heuristic. Okay. So, thank you.
More questions?
Thank you very much, Jessica. And I guess that my question is quite natural, because first, Angel this morning, he introduced the sim heuristics, now the learn, and now the next step seems that some kind of dynamics together with random inputs brings to all the community to something like sim learn heuristics. Can you tell us something about that? And the methodologies that in that case it would be needed? Because it seems that in every step of this construction, step by step, you need to change the distribution that it is in some case updated in every, okay? The demand is random, but the parameters of the distributions are being updated depending on, okay, the evolution. So then, can you please tell us something about that? Thank you.
It's a natural extension. It's things that you think. I have similarity, learners, I go to use all together. But I think it's not so easy, because we have not, at least I'm not using this approach. I think that Angel is trying to mix both approaches with some of the. Okay, so maybe she is the best, or Angel is the best to answer your question, because I'm not. I have not tried to perform this mix together, but I think that there are many things to consider in that combination. Maybe you can say something.
Yes, I think that the goal here to develop more realistic or more flexible tools to solve the more realistic problems, as realistic as possible. So in real life problems, you may expect that they're going to have uncertainty and dynamism. So both things are important. Imagine, for instance, traffic in smart cities, or air traffic, whatever. So yes, this is the long-term goal. So for the moment, we are focusing on semi-heuristics. I think we have learned a lot of semi-heuristics in the last years, also with the help of Jessica, Elena, and everybody. And now we are starting the research line with Learning Heuristics. I think it's a very promising research line. But our final goal is the unification of both theories. I think it's not so much difficult. It can be done, but we will need people really smart. So that's why we hired Marta here. So.
Right. Thank you so much.
Okay, any more questions? Okay, thank you so much, Jessica. So we're going to start tomorrow at 9:30 with Fatou Shava. I thank you very much him that he could come in the last minute to fill the space that Celso is doing better. So we're glad about this. This is the most important. So 9:30, and if you go to the dinner, you have the invitation. So for those who have invitations, you can see you at 8:30 at the restaurant. Okay, it's by the beach. It's a walking distance from here. Okay, thank you so much.